Welcome. Here we are now in Chapter 6, Sequences and Series of Functions. We will just dip our toe a little bit into Chapter 6. In fact, we'll only cover 6.2 and 6.3, so I won't even bother with doing the typical 6.1 discussion. But 6.2, we will talk about uniform convergence of a sequence of functions. So we've seen sequences of numbers. Now we think about a sequence of functions. And how can a sequence of functions converge to another function? There are a couple ways. There is pointwise convergence and uniform convergence. So we'll see these two ways and the differences between them. Pointwise convergence. This is the most obvious basic way, the kind of intuitive way that we think about convergence. So what does it mean to say that a sequence of functions, say f1, f2, f3, converges to a function f? We might write this using our parentheses notation, or the limit as n goes to infinity, fn. And here's our official definition. For each n in my natural numbers, let f sub n be a function defined on a domain A in my real numbers. The sequence of functions converges pointwise on A to a function f if, given any c in my domain A, the sequence of real numbers f sub n of c converges to f of c. Here's how I think about it. I have a picture, and there's some function f that is the limit of my other functions. And so my other functions might be, there's f1, f2, f3, f4, but eventually these guys are all converging down to f1, f2, f3, f4. So the idea is that if I pick any c in my domain, then I look at f1 of c, that has a y value, f2 of c, f3 of c, f4 of c. Those y values are eventually approaching f of c. And this will happen for any c that I pick. f1 of c, f2 of c, that sequence of points approaches f of c. Here's a symbolically given example. Consider the function fn is x squared plus nx over n. So f1, f2, f3, f4, and so on. And you can see perhaps where this is going. What does the limiting function look like? It is just x. So there's my f of x. And the idea is that for any fixed value of x, as n goes to infinity, my functions f sub n of x turn into f of x. So that's pointwise convergence. Let me show some examples of pointwise convergence a little more graphically. So we often think about it as one function that converges to another. So here's an example. This function looks like x squared, and a sequence of functions is going to turn it into something else, and in the long run it looks like it has become sine of x. That's kind of cool, right? Sine of x, and we can convert that between sine of x and x squared. So here's f1, that's what f1 is, and my limiting value f, and slowly one function turns into the other. The idea is also that this is happening vertically, that if I pick any point c, let me go back to the beginning again, that the y value of my functions is converging to the y value of the limit. My functions don't have to be continuous. Here's another example. In this case, I start off with sine, and I'm going to make a series of a sequence of functions that converges to the greatest integer function. There it is. It just splits up and meets. So one function converging to another, really a sequence of functions that converges. So a sequence of functions that converges to the greatest integer function. Here's one last example. This one maybe is a little bit boring, but we'll see it again later on. This is the function 1 over 1 plus x squared. And it converts into just 0, the flat function. All right. Let's take a look at this particular example, the limit of x to the n on the closed interval from 0 to 1. So here it is with n equals 1, and I can make n equals 2. There's x squared, x cubed, x to the 4th, to the 5th, and see how the shape is changing. Where is this limiting process taking us? What is the end result of all this sequence of functions? Well, the function is getting mushed down against the y-axis, right? And you can probably believe that anything between 0 and 1 will be the result eventually down the road of this sequence of functions. But what's happening at the point 1, 1? The point 1, 1 is fixed. That's not changing at all. So even though every other y value is coming down and getting pushed against the y-axis, the point 1, 1 stays exactly where it is. Consequently, the end result of this is the picture. Okay, I'll have to draw it out here. It's the picture. I've got 1, 1. That dot stays there, but everything else is along the x-axis. So it is a discontinuous function at the end. It's all zeros except at 1 where it has a value of 1. Here's another example. Let's see, x over 1 plus x to the n on 0 to infinity. All right, so here's n equals 1, n equals 2, 3, 4, so on. And here too, something strange is happening. To the left of 1, it looks like it's just becoming the graph of x. And to the right of 1, it's 0. And in between, right at 1, what's happening? It looks like there's also a fixed point. Can you see that fixed point is right at about 1 comma a half. In fact, what happens if I plug in 1 into this function? I'm going to get out 1/2. So the limiting value of this thing, the picture at the end, what's the limiting function? It's just at 1, it's a value of 1/2. Before that, it's simply y equals x, and after that, it's y equals 0. So the upshot of this, the strange thing, is that the limit of continuous functions need not be continuous. Here's our big thought. The limit of continuous functions need not be continuous. And that's not like a limit of x values. This is a limit of a sequence of functions. Many, many different functions that all converge to one particular function. The thing that they converge to might not be continuous, even if every function in that sequence itself is continuous. I have one more example of something weird that can go on with the convergence of a sequence of functions. Consider this sequence, G1, G2, G3, G4. Believe it or not, this sequence of functions converges pointwise to the flat line that is G at the bottom. And you can convince yourself by just picking some value of C and seeing what happens to the points. G1 of C is up there, G2 of C, G3 of C, G4 of C, and so on. And this sequence of points is converging down to G of C. If I take some point to the left, this C here, well, see, I've got G1 of C there, G2 of C goes up, G3 is even higher, but then G4 comes down because the wave has passed. And then G5 will be there, and G6, G7, G8, G9, G10. So eventually all these points do head down to G of C, and so on. So even if I took my C really close to the left side, G1 of C starts low, G2 of C is higher, 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 higher. Eventually I go way up to the top, then the wave would pass, and would come back down, 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 and eventually hit on the flat line again. So in a very weird way, as this wave is passing from right to left, all the y values really are eventually heading down to the flat line. But this looks weird, right? We don't want this. We don't want to imagine convergence of functions where my functions sort of stay away from the limit no matter how far down the sequence I go. What I'm seeing is that even if a sequence of functions has a limit, the individual functions in the sequence might forever stay away from the limit. And that just seems weird. We don't want that. So this is where the idea of uniform convergence comes in. I'm going to demand that my sequences really do get close to my limiting sequence in a certain way. Here's the picture that I'm after. I imagine my limiting sequence f, and I take a little bit above it, a little bit below it, so f plus epsilon, f minus epsilon, and eventually I want some term of my sequence, some function in that sequence, to be entirely within the epsilon bounds. We want the sequence of functions to approach f so that for any epsilon greater than 0, there's some n so that f sub n is within epsilon of f, and that's for all x. Here's our official definition of uniform convergence. Let f sub n be a sequence of functions defined on a set A contained in R. Then the sequence converges uniformly on A to f if, for every epsilon greater than 0, there is some big N in my natural numbers so that little n greater than or equal to big N implies that the difference between the term function and the limit function is less than epsilon. And this last absolute value really means that the bound works for all x in A. Here's an example, in fact one that we saw earlier. Let g sub n be the function 1 over n times 1 plus x squared. And we claim that gn converges uniformly to 0. It's no surprise that it converges to 0 because as n goes to infinity, this denominator will grow and I'll eventually end up with 0. But it's the uniformly part that's interesting to us. So here's our proof. First, notice that 1 over 1 plus x squared, that's the outermost function here. 1 plus x squared, that's my g1. And that is less than or equal to 1 for all x. So it kind of has a natural bound already. Next, let's observe that the difference between one term of my sequence and the limit is in fact the absolute value of that term, which is less than or equal to 1 over n, because of course the 1 over 1 plus x squared is less than or equal to 1. So I'd like to show that this guy is less than epsilon. I can make it arbitrarily small. So let an epsilon be given, and I'm going to choose big N greater than 1 over epsilon. Then, for any little n greater than big N, we will find that the difference of the term function minus the limit function is less than or equal to 1 over little n, there it is, which is less than or equal to 1 over big N because of this relation, which is then less than epsilon because of that. Oh, so I've done it. I found the big N that forces the difference between the term and the limit to be less than epsilon. And that proves that this sequence converges uniformly. Here's an example where one function converges to another, but it's not uniform convergence. I won't go through a formal proof, but I'll show this in GeoGebra. The function is this x plus 1 over n x squared. Can you see where that's going as n goes to infinity? That's really just converging to x squared, but it does it in a little bit of a funny way. Here we go. So this is the function when n equals 1, and then for n equals 2, 3, 4, 5, 6. So slowly the graph is moving to the right. Let me start that over again and you can take a look. So it starts here, and then as n increases, it shifts to the right. And eventually you can imagine, as n goes to infinity, this denominator gets arbitrarily large, and I just end up with x squared. So the end of all this is going to be the orange curve, the x squared. And so it looks like the function is coming in from the left, but don't be fooled, that's just an optical illusion. Remember that our convergence really happens pointwise up and down. So you can see that the blue point does match up to the limit function anywhere I choose. Alright, so let's put some epsilon bounds around the limit function, epsilon around my x squared, and I'll hide the x squared for right now. Does it happen that as n is increased, will I ever get entirely within those epsilon bounds? And yeah, maybe it seems like it can, but on the other hand, not really. If I'm always shifted just a little bit to the left of center. And since there is that shift just a little bit to the left of center, it turns out that I'll never be squarely inside of the epsilon bounds. So in fact, if I zoom out and I look far enough along the parabola, I'm sure I'll find a point, if I zoom in now again, look at that, where my function has slipped out of the bounds. It's just not there anymore. All right. And that will always happen, no matter how close I get, as long as I don't actually, if I can't actually get to my x squared, eventually way up high, the function is going to slip outside of the epsilon bounds. A Koshi criterion for uniform convergence. I like this because there's a really nice analogy with what we saw earlier in convergence of sequences of real numbers. And the great thing about the Koshi criterion is that we don't have to know an actual limit to show that the sequence converges. So here's our theorem for sequences of functions. A sequence of functions, f sub n, converges uniformly on A if and only if, for every epsilon greater than 0, there is some big N in my natural numbers, so that for all x in A, m and n being greater than big N implies that the difference f sub n of x minus f sub m of x is less than epsilon. So, to be honest, we're not really going to use this criterion all that much, but I include it because it's just kind of neat to see that the same sort of thing that works with numbers also works with functions. Now, our very final theorem is one that is important. The continuous limit theorem. Let Fn be a sequence of functions that converges uniformly on A to a function f. If each Fn is continuous at C, then f is continuous at C. So this really is the great theorem that we are hoping for. Earlier we saw examples where continuous functions were converging to a limit function that wasn't continuous. And that just seemed kind of weird and undesirable. But this is a great situation, and it tells us the power of uniform convergence, that if these functions are converging uniformly, then if they are continuous, then that characteristic will be shared by its limit as well. It's great when the limit has a characteristic that's shared by all of the terms in the sequence. The proof is not bad. It fits on this slide, so let's take a look. Fix some point C in the domain A and let epsilon greater than 0 be given. Choose a big N so that f sub n minus f is less than epsilon over 3 for all x. Why can I do this? I can do this because the sequence converges uniformly. So since the sequence converges uniformly, I know that such a big N exists. Somewhere down the road I can go far enough in my sequence so that for all x, the difference between f sub n of x and f of x is as small as I want. So epsilon greater than 0 was given already, so I can overshoot if I'd like, and I can demand that the difference between the term of the sequence and the limit of the sequence is less than epsilon over 3. All right. Well, here's something else I can do. I can say that there exists a delta greater than 0 so that x minus c less than delta implies f sub n of x minus f sub n of c is less than epsilon over 3. Why can I do that? I can do that because each f sub n is continuous at c. What does it mean for a function to be continuous at c? It means that if the difference between x and c is less than delta, then the difference of the function values can be made small. And I can make it as small as I want, and epsilon is given to us, so I can overshoot if I'd like, and I can choose a delta so small that it makes the difference in my function values less than epsilon over 3. Okay, let's remember what was the goal. Our goal is to show that the f function was continuous at c. So I need to show that the difference in these function values is arbitrarily small. Can I show that this difference is less than epsilon? So here's a trick we've seen before. It's a good trick. I will add and subtract the same thing, but this is very clever. I'm going to do that twice in this expression. I'll subtract and add f sub n of x. I'll subtract and add f sub n of c. And then this expression breaks into the sum of 3 absolute values by the triangle inequality. And I claim that each of these 3 absolute values is less than epsilon over 3. So let's take them each one at a time. F of x minus f sub n of x. Why is that less than epsilon over 3? Oh, well, that was this inequality here due to the uniform convergence. So that was because of 1. Now what about my middle? Why is that less than epsilon over 3? That's because f sub n is continuous. It's because of that inequality there. And how about my third absolute value? You know, once again, this is less than epsilon over 3 because of number 1, the fact that I have the uniform convergence. Here it's just this particular c value, whereas previously I had x in general, but that doesn't matter. And so that tells us epsilon over 3 plus epsilon over 3 plus epsilon over 3, that is epsilon. The difference of my function values with the f function is less than epsilon, and that's exactly what I need to show that the limit is continuous. Hey, that's really cool. That is a nice theorem, that when my functions converge uniformly, then if the individual functions themselves are continuous, the limit will also be continuous. So use that idea, perhaps, in a homework problem or two. Take a look at these problems, give them your best efforts. Read the book. Don't forget, the book is pretty good. It has lots of nice examples that you can follow to think about and use as you try the homework problems. And of course, continue asking me. I have enjoyed helping you, those people who have contacted me on Zoom, and I'm always happy to keep on doing that. So ask if you have questions. Thanks.